have generalized coordinates, which are theta and r. So the first question says, what is the mass moment of inertia of the pendulum about point O? So we're looking for moment of inertia about O here at the pivot point. Okay, and then they say we have to use the generalized coordinates theta and r as defined in figure Q1. Okay, so what we're going to do here, we're gonna check what is there on the pivot point. So at point O, we have a slender rod around one end. It's at one end, okay, and then the moment of the rod of this slender rod is gonna be the moment of the rod is gonna be 1/3 ml squared. The reason why it's 1/3 is a rod. When the rod is at the end, the moment of inertia is 1/3 ml. When the rod is at the center, it's 1/12 ml squared. I don't know if you still remember that. If the rod is at the end, it's gonna be 1/3, and if it's in the center, it's gonna be 1/12 ml squared. So our rod is at the end, that's why we have 1/3 L squared. So on our figure, we also have a sliding mass at point O. So that's sliding mass is moving along the pivot point O. So the moment of inertia of that mass is gonna be I for mass, the sliding mass. So I'm gonna use a big letter M for sliding mass and the small letter m for what? For the slender rod. Okay, so the big letter M is for sliding. So the moment of inertia of the mass, the sliding mass, is gonna be m r squared. Okay, mr squared. So for the rod, it's 1/3 ml squared, and then for the sliding mass, it's gonna be mr squared. So now they want us to determine the total moment of inertia around point O. So you just take a look on your system and check which which system are acting around that pivot point. So we have the rod, we also have the mass that are acting about point O. So now we got the moment of inertia of rod and mass. So after that, we're gonna get the total moment of inertia around point O. So it's gonna be I around pivot point O equals to I rod, moment of inertia of the rod, plus moment of inertia of the mass, sliding mass. So now we're gonna have 1/3 ml squared plus mr squared. And then now we are done with the first question, 1.1, the one that they say we should determine what? The moment of inertia around what? Around pivot point. So the most important thing here, you just have to understand the question and take a look on your system, analyze it, okay, and also know the Lagrange equation. I think that's the important thing. Okay, so now we're done with the 1.1, where they say we have to determine the moment of inertia around point O. Okay, and then 1.2, they want us to determine what? The nonlinear equation using Lagrange. Do you have any question before we do 1.2?
Yeah, they say use the generalized coordinates theta and r, so there's no need to use that theta. I say we used r.
Let's go back here. 1.2. So
1.1.
Oh, 1.1. No, there's no need. We're gonna use the generalized coordinates on 1.2. The L and the theta. Sorry.
Okay, no problem.
Yes, it's only 2 marks, so there's no need to do a lot of things. So the generalized coordinate, we're going to use it at 1.2 when we are determining what the nonlinear equation, defining the motion of pendulum using what Lagrange approach. So here we're going to use the Lagrange equation, the T minus U, the potential, kinetic energy minus potential energy. Okay, this one is for 10 marks, so we have to do a lot here. Okay, so let's move forward and do 1.2. So now we want the equation, the nonlinear equation, and then they ask us to use what? The Lagrange equation. Sometimes they'll say use any method. When they say use any method, you can use the Lagrange equation. You can also use Newton's second law. You can also use Newton's second law. So now here they tell us that we should use what? Lagrange. So we all know that Lagrange equation is derivative of d of time, and then partial derivative of kinetic energy over partial derivative of the velocity minus partial derivative of kinetic energy plus potential equals to QI. Remember, the QI is for the force. If we have force, we're going to equate with the force. If we don't have, it's going to be equals to 0. So now what we're going to start with, we're going to start by looking for kinetic energy. Remember, we have the T and the U. So we're going to start by looking for T and then U. So the kinetic energy of this system is going to be kinetic energy. So we're gonna look at our system and check what's our kinetic energy. So we're gonna have the kinetic energy on the rod. We're also gonna have kinetic energy on the sliding mass. So we're gonna have T rod equals to half moment of inertia of the rod theta squared. Now you can see we are using the generalized coordinates of what? Of theta, because our rod is connected to what? To theta. Okay, and then we're gonna also have kinetic energy of the sliding mass. So we're gonna have kinetic of big letter M, the sliding mass, which is equals to what? To half mv squared, like this. Okay, and now we know that the moment of inertia of rod is equals to what? Is equals to 1/3 ml squared. So here we're gonna substitute with the moment of inertia of rod. So T rod equals to half into 1/3 ml squared multiplied by what? By theta dot squared, like this. So every time when we are writing kinetic energy, we use what we call the generalized coordinates. So when we write kinetic, the generalized coordinate is supposed to have what? The dot, to show that it's what? It's velocity. So I'm lying, there's no dot here, it's just mv. Is it mv dot square? Just remember, but I think it's mv only. There's no dot. Let me confirm first. I think it's only V. No, it's V dot square. So our kinetic energy of the rod, it's what? It's 1/2 multiplied by 1/3 ml squared theta dot square forward for the rod, and then for the mass it's half mv squared. So we're gonna look for the V. We're gonna look for V squared. So to get the V squared, we're gonna use what do you call the right angle triangle. As you can see from our diagram, we have the theta here, so it can form what? the right angle triangle, we're gonna have the x and the y. So velocity square is equals to what? To x dot square plus y dot square. I don't know if you still remember this. The right angle triangle. Let me show you what I'm talking about.
Okay. Yeah, can you please show me?
Yeah. So now we're done with the kinetic energy for the of the rod, okay? And now let's focus on the kinetic energy of what? Of the sliding mass. Okay. So we have Tm is equals to 1 of 2mv squared. I think that v doesn't have dot. It does. I think it does. But I'll check again. But I think it does have the dot. Okay, so to get the v dot square, we're gonna focus. We're gonna check on our triangle. So our theta looks like this on the diagram, right? And then we can draw a right angle triangle. So our right angle triangle is gonna be like this, and then we're gonna have what? This side we have r, okay? And then the 90 here. So from that diagram, our right angle triangle is gonna look like this, where we have r here, and then here we're gonna have theta. So we're gonna have the x, and then we're also gonna have our r. I think is on the hypotenuse.
The hypotenuse.
Yes, it's this side. Then we're gonna have the x and the y. Okay. Our r is this side. So v squared, it's equals to x dot squared plus y dot square. Okay. I think it's dot here. I think we do have a dot, but I will recheck. So our v squared is equals to x squared, y squared. But here on our right angle, we only have y and x. We don't have dot. The dot is for velocity. Here on our right angle triangle, we only have displacement. We don't have velocity. So now let's find x and y. To get x and y, we're gonna use trigonometric. Okay, so remember the theta is here, which means these two sides, they're gonna swap side. So here where it's adjacent, it's gonna be opposite, and then this side is gonna be adjacent because the angle is here. So which means our x is gonna be what? Adjacent over this one is adjacent, and then this one is gonna be opposite. Yes.
Yeah.
And then our x is gonna be x over r. X over r is equals to opposite over hypotenuse is gonna be sine, so it's gonna be sine of theta. And then this side is gonna be y over r. Adjacent over hypotenuse, it's what? It's cos of theta. So our x is equals to what? R sine theta. And then our y is equals to what? R cos theta. And remember, we are looking for x dot and what? And y dot. So the dot stands for derivative. So we're gonna derivate our x, and we're also gonna derivate our y. So we're gonna derivate our x with respect to r and theta. Okay, so we're gonna use the product rule. You know the rules of derivative, right? We have the quotient, we have a product, we have chain rule. Like we have different types of derivative rules. So here we're gonna use the product rule. So the product rule, we copy the first, and then we derivate the second, and then we copy the second and we derivate the first. I don't know if you get it. So the derivative of x squared, of x, derivative of x is gonna be, we're gonna copy, let's copy the second one, copy sine theta and derivate r. Derivative of r with respect to x is gonna be r dot. Okay, and now after plus, remember we start by copying sine, Now we're going to start by copying what? R, and derivate what? Sine. So the derivative of sine is what? It's cos with respect to what? With x. So it's going to be R, we copy R, and then we derivate sine with respect to what? To x. So it's going to be cos of theta multiplied by what? By theta dot. Remember, here on product rule, we're going to derivate the x with respect to r and with respect to theta. That's why here we have the theta dot. Okay, so we derivated the cos theta with respect to theta, and then we derivated the r with respect to, we derivated x with respect to r, and then the second part we derivated theta with respect to x. So okay, now we have this. When we derivate x, we have sine theta r dot plus r cos r cos theta times theta dot. Okay, did you get this?
No.
Did you get it?
Yeah.
Okay.
I think I get it.
And now we are using product rule. Product rule, we copy, we derivate, we copy, we derivate. Okay, and then on the y, let's derivate y. Remember, we copy and we derivate. Let's start by copying what? Cos. Gonna copy cos and derivate what? R. The derivative of r with respect to y is gonna be what? R dot. It's gonna be r dot. Okay. Plus, we started by copying cos theta, and now we're gonna copy r. Okay. So we copy r and derivate cos. The derivative of cos theta is what? It's going to be a negative sine theta. So we're going to have multiply by a negative sine theta. Remember, we are derivative with respect to theta. So it's going to be multiplied by what? By theta dot. Okay? Like this. Remember, it's derivative with respect to r and theta. R and theta. So now we have our x dot and our y dot. We can substitute back to our x dot squared and y dot squared. Remember, our kinetic energy of the sliding mass is half mv squared. And now here we're looking for what? For v squared. Okay, and then our v squared is equals to x dot squared plus y squared. The reason why we have x and y is because we have the angle. And we know if we have the angle, we have to have components. You know, components is sine and cos theta. Okay, that's why we have x and y. It's because of this angle.
Okay.
Yeah. So moving forward.
So every time we have an angle, this is what we must do.
Yes. When we have a pendulum, this is what we do. And then sometimes we can have an angle, but it's a translational system. We're not talking about translational system. We're talking about the mass with the spring and another mass. Sometimes you'll find, okay, on that translational system, we have an angle. There's no need to do this v squared x squared plus y squared. I think it's also depending on the method that they ask us to use. Okay, so sometimes they'll say use any method. So on the Newton's second law, you can use this method. You can use this v squared x squared plus y squared. We only use it on the Lagrange method. Okay. Yeah, so moving forward, we're gonna substitute these values, x dot and y dot. Okay, we're gonna have a v dot square, which is equals to, we have x dot square plus y dot square. Okay, our x dot, it was r dot sine theta plus r theta dot cos theta. Okay, all squared, plus y dot, our y dot, it was r dot cos of theta minus r theta dot sine of theta. The negative is coming from derivative of cos theta, so the derivative of cos theta is sine theta, is negative sine theta. Okay, all squared. And now we can open two brackets and then we multiply. So we're gonna end up with the v dot square as r r dot square plus r squared multiplied by theta dot square. After simplifying this, we'll end up having sine square theta plus cos square theta, and then we know that this is equals to what? Is equals to 1. That's why we have r dot square plus r square multiplied by theta dot square. Okay, when we multiply this, we're gonna end up with something like this, which is gonna be equals to what? Equals to 1. And then we're also gonna have a negative 2r r dot sine theta cos theta plus 2r r dot sine theta, and then it's gonna cancel each other. That's why we end up with this equation of r dot square plus r square theta dot square. So therefore our TM, our kinetic energy of sliding mass, is gonna be 1 over 2m into r dot square plus r squared theta dot square, like this. So we have the kinetic energy of the rod. We also have kinetic energy of sliding mass, and then we want the total. So the total, we just add the rod and the mass. Therefore our kinetic energy is gonna be T rod plus Tm. Our T rod, it was 1 over 2 into 1 over 3 ml squared. Okay, theta dot square. Okay, this dot here, plus the kinetic energy of the mass, which was half m into r squared dot plus r squared theta dot square, like this. So this is our kinetic energy of that system, where we have a slender rod and a sliding mass and a pivot point at O. So this is our kinetic energy. We are done with the kinetic energy of our system, and now let's do potential energy. Okay, so on potential energy, we have mass m at a distance r from that where's that? We have this mass, the big letter M, from this distance, at distance r. You can see the distance r. Okay, so it is a center of what? Of gravity of the rod, of this slender rod. Okay, and then it is going. I'm saying we have the mass, this M, the big letter M. Okay, at the distance r. You can see, right? At the distance r. So it is a center of gravity of the what? Of the rod. It is going to be what? A half of the length. So we're going to divide this L with 2. Okay, because it's what? Is the center of gravity. So our potential energy of this mass is going to be the mgl over 2, because it's what? Is the center of gravity. So we're going to divide it by 2. So our L is going to be L over 2. So this potential energy, the potential energy of this mass is going to be what? mgl over 2 into 1 minus cos of theta. For the pendulum, remember pendulum is, it's moving back and forth. It's more like what do you call merry-go-round? Is it merry-go-round? A string. It's more like a string. Yes, it's going back and forth. So that's why we have the L. We're gonna have the 1 minus cos of theta, L over 2 into 1 minus cos of theta. I don't know if you attended last tech class when we were doing pendulum. I was explaining pendulum in details, showing you guys how to get the 1 minus cos theta, the length, where we have the h, changing h is equals to 1, is it 1 minus cos of theta, L into L cos of theta, something like this.
I think I attended it.
It was like this, where we have a pendulum here, and the length and then we have a distance like this, and then we say here it's h, and then we have another l, and then we say change in h, it's equals to L minus L cos of theta, and then that's where we end up with L into 1 minus what? Cos of theta. But now our M is in the middle, like it's moving on our on the cylinder rod. That's why we're gonna divide L by 2. Is at the center of gravity of the rod. Okay, so our potential energy of the mass is gonna be like this. Of the rod, so it's gonna be mg L over 2 into 1 minus cos of theta. Okay, so it's 1 into cos of theta. Okay, and also we have a rod. So plus mg r into 1 minus cos of theta. So this is the potential energy of what? Of the rod. So this one is when we have the center of gravity, so it's in between. So we divided the L by 2, and then now we have the one with the rod, with the r, so it's mgr into 1 minus cos theta. And then remember, we are also given a spring. So we're also going to have a potential energy of what? Of the spring. So U of S stands for spring. So we know that potential energy of spring is half K x squared. So the x is what? Is extension. So the x is going to be R minus LO squared. Remember, they said the spring is unstretched length of LO. So it's in between the R and the LO. So that's why our x is equals to what? Is equals to R minus LO. X is the extension. Okay, we have the R and the LO on our spring. So we're gonna subtract it. Therefore,
so isn't it? Why is it R minus LO instead of LO minus R? Won't LO, or LO is the initial, ne?
Yes. They said, where is it? They said the spring has a stiffness K and unstretched length LO. Like it's unstretched LO. From the general, okay, it's fine. We have this R, okay, and the length of the spring. Okay, so it's gonna be R minus what? The LO squared. The extension of the what? Of the spring. Okay. Moving forward, our US is gonna be half K into R minus LO squared. Okay, and then therefore the total kinetic energy is gonna be the U rod plus the spring one, the kinetic energy of the spring. So we have mgl over 2 into 1 minus cos of theta, and then we have plus mgr into 1 minus cos of theta plus the spring 1 over 2 K into R minus LO all squared. Okay, so this is our kinetic energy, our potential energy, and then our kinetic energy, it was 1 over 3 ml squared plus 1 over 2 m into R squared dot plus R squared theta dot square, like this. Okay, and now remember, they say we have to determine the nonlinear equation using what? Lagrange equation. So on our Lagrange equation, remember, we have d over dt, partial derivative with respect to time, So now here we're going to use the theta and the r. Remember I said Q is for displacement. Our displacement is theta and r. So we're going to have two equations. We're going to have two nonlinear equations because of generalized coordinates of theta and r. So we're going to start with the theta and then r. Okay. Wherever there's Q, we're going to substitute with the theta. And then after determine the first equation, the second equation, wherever there's Q, we're going to substitute with r. Okay, so minus dt of partial derivative of qi plus partial derivative of u qi is equals to 0. Why we're equating to 0 is because on our system we don't have what? Any force. We don't have any force. Okay, if we had a force, we're going to say equals to 0. Equals to the force that we were given. Okay, so now I said on the Q I, we're going to start with the theta. So wherever there's Q, we're going to start with the theta. So here, because we have the dot, it's going to be partial derivative of kinetic energy over partial derivative of the theta dot minus partial derivative of kinetic energy over partial derivative of theta plus u over partial derivative of theta equals to 0. And then we're going to derivate this equation with respect to what? With respect to theta. So wherever we have a theta on the kinetic energy, here we're going to derivate it. Wherever there is a theta, we're going to derivate it. Even on the potential energy, wherever we have the theta, we're going to derivate it. Okay, so now let's start with the theta. We're going to have d over dt into partial derivative of kinetic. This going to start with the theta. Okay, now going back to our equation, we're gonna start by checking at what? At kinetic energy. Partial derivative of kinetic energy with respect to theta dot. So wherever there is a theta dot, we're gonna derivate. Okay, so let's derivate. We're gonna focus here. We're gonna check where is a theta dot. Our theta dot, it's here. Okay, so our theta dot, it's here. We also have a theta dot here on the kinetic energy of our rod. It's half into 1 over 3 ml squared theta dot square, right? So we have the theta dot here on the rod. We also have a theta dot here on the sliding mass. So when we derivate, let's start by multiplying these two. So it's going to be 1 over 2 multiplied by 1 over 3 is going to be 1 over 6. 1 over 6, it's going to be 1 over 6 ml squared theta dot squared. Okay, for this one, it's going to be 1 over 6 ml theta dot square. So when we derivate with respect to theta dot, it's going to be what? 1 over 6 multiplied by 2. 1 over 6 multiplied by 2 is going to be 1 over 3 ml squared theta dot. Because we took this squared and multiply with 1 over 6. So 2 multiplied by 1 over 6 is 1 over 3. So it's going to be 1 over 3 ml squared theta dot. The square, it's gone. Okay, because we derivated. Okay, after that, we're going to also check the one that have a theta dot. It's this one. Okay, it's this one. So, it's this one. So derivative of half m r squared theta dot square, it's what? It's gonna be 1 over 2 multiplied by 2. It's gonna be m r squared theta dot. Right? Because 2 multiplied by 1 over 2 is 1. So it's m r squared theta dot. Right?
Can you repeat?
I'm saying we're gonna derivate wherever there's theta dot, we're gonna derivate. Okay, we start with the rod, so we multiply this 1 over 2 and 1 over 3, and then we got this, and then when we derivate 1 over 6 ml squared theta dot square, we get what? 1 over 3 ml squared theta. Okay, because we derivated this, and then now we're gonna check theta dot square again. Theta dot again. So our theta dot is here. So we have 1 over 2 mr squared theta dot square. So when we derivate this, like we have this mr squared theta dot square. So we're gonna derivate this with respect to theta dot. Therefore, after derivating, we're gonna have mr squared theta dot. Okay, because we're derivative with respect to what? With the theta, right? Yeah. We're here, we were derivating. So after derivative, the first theta dot, we had 1 over 3 ml squared theta dot, okay, plus mr squared theta dot, like this, okay, minus, and then we're gonna go back to our kinetic energy and check where there is only theta, the one that doesn't have a dot on top, and derivate with respect to theta, the one that doesn't have a dot. So from our kinetic energy equation, we only have a theta dot, we don't have only theta, so which means it's gonna be 0. Do you get it?
For potential energy.
Yeah.
We're still on kinetic.
Yeah, for kinetic energy. Remember, we are here. Here.
So we don't have a theta.
Yeah, we don't have a theta, so it's gonna be 0. It's gonna be 0. Plus, and then now we're going to focus on what? On potential energy. We're gonna focus on potential energy only. So going back to potential energy, this is our potential energy. Remember, we're starting by what? By theta. We're gonna focus only on theta. Only on theta, which means we're gonna derivate wherever the theta, we're gonna derivate. So mgl L over 2 into 1 minus cos of theta. So the derivative of this part is gonna be mg L over 2 multiplied by what? By sine cos. Derivative of 1 is 0, and then derivative of negative cos theta is what? It's negative sign, so it's going to be negative multiplied by negative, which is going to be a positive sign of theta. Ane?
Yeah.
Okay. So now we are derivating potential energy. So we're going to have mg L over 2 sine of theta. So the sine of theta is from here. Derivative of 1 is 0. Okay.
So when we also, don't we just leave that 1 that's in the bracket and just derivate the cos?
Why do we leave it?
Since isn't it a partial derivation? So don't we only focus on cos?
Yeah,
no matter the 1 becomes a 0.
Yeah, because derivative of a constant is 0, and then derivative of cos, it's what? It's negative sign. So therefore we're gonna have what? A sine theta. That's why when we derivate mg L over 2 into 1 minus cos theta, we get what? We get mg L over 2 what? Sine theta. Okay, that's it. This is where we get the sine theta. We get it from here. Okay.
Okay, yeah.
And then we also have mgr 1 into 1 minus cos of theta. So we're gonna have plus mgr sine of theta. And then remember here, this is the derivative with respect to time. Derivative with respect to what? To time. So here we're gonna derivate with respect to time of what? Theta dot and the r squared. Okay, so the derivative of 1 over 3 ml squared theta dot with respect to time is gonna be what? It's gonna be 1 over 3 ml squared theta dot dot. When we say derivative with respect to time, we are talking about acceleration. When we have 2 dots, it means acceleration. When we have 1 dot, it's velocity. When we don't have any dot, it's displacement. Okay, so now we are done with the first kinetic energy. Now moving forward to mr squared theta dot. Here we're gonna derivate with respect to r and with respect to theta. So we're gonna start with respect to theta. So it's gonna be derivative of mr squared theta dot with respect to time. It's gonna be mr squared theta dot dot. Okay, theta dot dot. And now we're done with the theta. Now let's focus on the r. So derivative of mr squared theta dot with respect to r is gonna be what? We're gonna take this 2 here. It's gonna be plus 2 mr, okay, with respect to time. So when we're derivating with respect to time, it's gonna be 2 mr r dot theta dot. Okay, so we derivated this mr squared theta dot with respect to what? To r. So we took this 2 and multiplied with the m, so it's 2 mr, and then we subtracted 1 here, then we're left with r. And remember, we are derivative with respect to what? With respect to time. That's why we have r dot. Theta dot, we just copied this one. Okay, do you get it, Kuriso?
No, can you please repeat that?
Okay.
That 2 mr dot theta dot.
Okay.
I think why are we getting r and then after that we put another
r dot? Okay.
Mm.
This one you get it. We were derivating with respect to theta. That's where we have a theta dot dot mr squared theta dot dot. So here we have the r squared and the theta.
Yeah.
And remember, they said that our generalized coordinates is what? Is theta and what? And r. So here when we derivate, we're gonna focus on r and theta. So we start by theta, and now let's focus on the r. To derivate mr squared theta dot with respect to r, we're gonna derivate r. So derivative of r squared is what? It's 2r, right? Derivative of r squared is what? Is 2r. Okay?
Yeah.
And then we have the m and the theta. So it's gonna be 2r m
yes.
theta. But we are derivating with respect to what? To time. We are derivating with respect to what? To time. That's why we're gonna have what? R dot, to show that we are derivating with respect to time. Get it? You got it? Did you go?
Okay.
Did you get it?
Yeah.
Silas?
I think I understand. With respect to time, I'm going to have to add another r
Dot.
With that velocity.
Yes,
yeah,
yes.
With that dot.
Yes.
Yeah.
Okay. So it's gonna be plus 2r m theta dot r dot. Okay. We were here. We were derivating with respect to time. We're derivating with respect to time, and therefore we have 1 over 3 ml squared theta dot dot plus mr squared theta dot dot plus 2r plus 2r m theta dot r dot. Okay, and then plus mgl over 2 sine theta plus mgr sine theta is equals to 0. So this is our first equation. Remember, they say we have to determine a non-linear equation. So this is our first equation. We were using what? Theta as our generalized equation. After here, we're gonna use r. We're gonna derivate with respect to what? To r, and get what? The second equation. Yeah. And then sometimes you'll Xavier will say, let's say our sine theta, it's approximate to what? To theta. So we can write our sine theta equals to what? We can write our sine theta as theta on what we call a small oscillation angle. We say sine theta is equals to theta. Okay, but so I think sometimes he mentioned in the question, or okay, we have a small oscillation angle. So when you say we have a small oscillation angle, which means sine theta is equals to what? Is equals to theta. Okay, if he mentioned it. So he didn't mention it, so we're gonna leave our first equation like this as what is 1/3 ml squared theta dot dot plus mr squared theta dot dot plus 2r m theta dot r dot plus mgl over 2 sine theta plus mgr sine theta. Okay, this is our first equation with respect to what? To theta. And now let's do the one that the generalized coordinates of what? Of r. So remember our equation is d over dt. Remember it's 10 marks, so that's why it's long.
Yeah.
And then partial derivative of t over r dot minus partial derivative of t over r plus this equals to 0. We don't have any force, that's why it's equals to 0. Okay, and now we're going back to our kinetic energy equation and check wherever there's r dot, we're gonna derivate. Okay, so, where is it? It's mixed up. So this is our kinetic energy. Wherever there is r, we're gonna derivate. Okay, wherever there's r, we're gonna derivate. Sorry, so here we have the r dot. Okay, so the derivative of 1/2 mr squared dot is gonna be what? It's gonna be mr dot, like this. The derivative of half m r dot square is gonna be mr dot. Okay, so it's gonna be d over dt into what? Into m r dot. Oops. Minus, we're gonna, yes, because we only have one r dot on our kinetic energy. And then going back to kinetic energy, we're gonna check the one that doesn't have a dot, the one that only have r. Okay, where is kinetic energy? It's here. So we have half m r squared theta dot square is this one. So the derivative of 1/2 mr squared theta dot square is gonna be what? We're gonna take this 2 and multiply with this one, so we're gonna have the mr theta what? Dot square. Okay,
Good.
yeah, and then we're gonna write it on our equation. So it's minus into m r theta dot square, like this, plus the potential energy. We're gonna go back to our potential energy. Wherever there's r, we derivate. Okay, going back to potential. I'm looking for potential. Okay, this is our potential. Yeah, we have a lot here. Let me reduce. Okay, so here on our potential, we're gonna look for r. We have the r here, so the derivative of mgr into 1 minus cos of theta. Remember, we're focusing only on the r, so it's gonna be the derivative of r, it's 1, so it's gonna be what? Mg 1 minus cos of theta. Okay, 1 mg into 1 cos of theta, because we derivated the r. And then we also have r here. When we derivate this, we're going to take this 2 and multiply with 1/2. So we're going to have what? K into r minus LO multiplied by what? By 1. The 1 is what? Is the derivative of r. And then any number multiplied by 1 is that number. Okay, that's why we're going to left with what? With K into r minus LO. Did you get it?
Yeah, I get it.
Okay, so therefore, the partial derivative of potential energy is going to be mg into 1 minus cos theta plus k into r minus lo. Okay, so it's going to be mg 1 minus cos of theta plus k into r minus lo multiplied by 1 is the same. Okay, then equals to 0. We're not done yet. We still have to derivate mr dot with respect to time. So it's going to be mr dot dot minus mr theta dot square plus k plus mg into 1 minus cos of theta plus k into r minus lo. So this is our second equation. When we have two generalized coordinates, which means we're going to have two equations. And if we have three generalized coordinates, we're going to have three equations. Okay? And then what time is it? It's 8 o'clock. 1.3, they want us to determine the inverse Laplace displacement response. We are given a Laplace equation as 3 over s into s squared plus 2s plus 5. This is long, but let's do it and then we're going to continue tomorrow. Okay, we're going to do half, and the other half we're going to do it tomorrow. So 1.3, they want us to determine what? The inverse Laplace. We're done with this one. The Lagrange approach. The L equals to T minus U. We're done with it. We got the nonlinear equation. We got two nonlinear equations. And then 1.3, they say a more experienced colleague proposed that after numerical substitution, the partial fraction decomposition of theta into s is theta into s is equals to 3 over s into s squared plus 2s plus 5. And then they say find the displacement theta into t response corresponding to theta s. And so we are given this numerical substitution. We're given this equation, and then they want us to determine what? To find the displacement. What we're going to do here, we're going to use partial fraction. You still remember partial fraction, right?
Yeah.
Okay, so we're going to use partial fraction to determine the displacement response of the Laplace. Okay. We have the theta as it's 3 over s into s squared plus 2s plus 5, right? Yes. So what we're going to do here, we will start by partial fraction. So to use partial fraction, we start by checking if we can simplify this. Factorize if we can factorize. So here we can't factorize s squared plus 2s plus 5. We can't. So if we can't, we're gonna use this formula for partial fraction. So we have 3. So we have 3 over s plus into s squared plus 2s plus 5. So our partial fraction is going to be what? A over s plus, since this one we can't factorize, it's going to be bs plus c over s squared plus 2s plus 5. Okay, like this. After writing partial fraction, we're going to multiply both sides by the denominator. Our denominator is s into s squared plus 2s plus 5. Okay, we're going to multiply both sides by denominator. So it's going to be 3 over s into s squared plus 2s plus 5. Okay, multiply by s into s squared plus 2s plus 5. All equals to a a multiplied by what? By s into s squared plus 2s plus 5 all over s, okay, plus bs plus c over s squared plus 2s plus 5 multiply by s into s squared plus 2s plus 5, okay, like this. So we multiply both sides by the denominator, and then this one and this one is going to cancel each other, and the s cancel each other, and then s squared plus 2s plus 5 is going to cancel each other. We're going to be left with 3 equals to what? A into what? Into s squared plus 2s plus 5, okay, plus bs plus c multiplied by what? By s, okay. And then from here we're gonna calculate for a, b, and c, okay. So we're gonna use what do you call simultaneous equation. Let's see if we're gonna use it. So first we're gonna multiply the a with the s squared and 2s plus 5. So we're gonna have 3 equals to as squared plus 2as plus 5a plus bs squared plus cs, okay. So we're gonna have 3 equals to as squared plus 2as plus 5a, okay, plus bs squared plus cs, okay. So here what we're going to do, we check on our left hand side and right hand side, and then we match. So on our left hand side we don't have s squared, so we're gonna group the s squared together and the s together, and the one that, can you hear me?
Yeah.
Okay, I was saying,
Can you hear you now?
yeah, I can hear you. So I was saying we're gonna match whatever that is on our left, we're gonna match it with the whatever that we have on our right. So first thing, we're gonna group the s squared together, and then the s together, and the one that doesn't have the s together. Okay, so it's gonna be 3 equals to as squared plus bs squared plus 2as plus cs, okay, plus 2a it's 5a plus 5a, yes, plus 5a, like this. So you can see on our left hand side we don't have s, so which means it's gonna be as squared plus bs squared is equals to 0, and then 2as plus cs is equals to 0, because on our left hand side we don't have any s, okay. And then we also have 3 is gonna be equals to 1 that doesn't have a s, so it's gonna be 5a. Therefore our a is gonna be equals to what? 3 over 5. Okay, we're done with the a, we got the value of a, and now let's look for b. So here we have as squared plus bs squared is equals to 0, so we can take out the common factor of what? Of s. So it's gonna have s squared into a plus b is equals to 0, and then we're gonna divide both sides by what? By s squared, and therefore we're gonna have a plus b equals to 0, because 0 divided by s squared is 0. And then we have the value of a, which is 3 over 5. Therefore b is gonna be a negative 3 over 5, right? So we are done with the b. And now let's come to s. So we're gonna take out the common factor of s here. So we're gonna have s into 2a plus c, all equals to 0. So 0 divided by s is 0, so it's gonna be 2a plus c, which is equals to 0. And then we have the value of a, which is 3 over 5 plus c is equals to 0. So therefore our c is gonna be what? A negative 6 over 5. So now we have the value of a, b, and c. We're gonna substitute back to what? To our partial fraction equation. You see, wherever there's a, we're gonna put 3 over 5. Wherever there's b, we're gonna put a negative 3 over 5, and wherever there's c, we're gonna put a negative 6 over 5. Okay, and then after here we're gonna do inverse Laplace. Remember, we are looking for what? For inverse Laplace displacement response. We're looking for theta t. So to get the theta t, we're gonna introduce inverse Laplace. We're gonna introduce inverse Laplace. Moving forward, we got our values. So remember, we had 3 over s into s squared plus 2s plus 5 equals to a over s plus bs plus c over this. So we have the value. So we have 3 over 5 multiplied by, we're gonna take this s on the side, so it's gonna be 1 over s. My 5 and s is the same. Okay, plus a negative 3 over 5 s minus 6 over 5 all over s squared plus 2s plus 5. Okay, and now we can now introduce what? The inverse Laplace. Here we can introduce the inverse Laplace. So we're gonna have a theta into t. Remember, we're looking for theta into t, so it's gonna be 3 over 5 inverse Laplace of what? Of 1 over s. Okay, plus inverse Laplace of this. But on our table we don't have something like this, so we have to simplify negative 3 over 5s minus 6 over 5 over s squared plus 2s plus 5. It's getting late. We're gonna continue tomorrow and simplify this. To simplify, we're gonna complete the square of what? Of s squared plus 2s plus 5. We're gonna complete square of this. Okay, so which is gonna be what? S squared plus 2 s multiplied by 1 over 2 all squared plus 5 minus 2 multiplied by 1 over 2 squared. So therefore, after completing the square, our answer is going to be s plus 1 squared, because 2 multiplied by 1 over 2 is going to be 1 squared. 1 squared is 1, so that's why we have s plus 1 squared. Okay, plus 5 minus 2 multiplied by 1 over 2 squared is 4. So after completing the square of this, we're gonna get this. Okay, and then that's where we're gonna what? We're gonna introduce the inverse Laplace. Okay, do you get it?
Okay.
Yeah, so we're gonna continue tomorrow.
Yeah, I get it.
Yeah, I'll scan my solution and send it to you. If you don't get it, if you don't understand, you'll ask question. Ne?
Okay, no problem.
But we'll continue tomorrow.
And then also send them another recording.
Yeah, I'm sending.
Recording.
A.
Okay.
Sharp.
Alright,